Number one is the RC circuit. When the switch is closed, the current will flow through and the voltage across the capacitor will rise. So it will look like this. This is the time and this is the voltage across the capacitor. And this line will be V0. And the equation is the voltage across the capacitor as a function of T is equal to V0. V0 is the voltage of your DC source. 1 minus exponential to the power of minus T over RC. Number two, after the capacitor is charged, you can now discharge the capacitor. So when the switch is closed, it will discharge. Now the voltage across the capacitor will start from V0 and exponential decay. So voltage across it is equal to V0 exponential to the power of minus T over RC. Okay, next, number three. If you have a inductor and a resistor, now when the switch is closed, the current, this time we measure the current. This is T, and the current passing through the inductor will rise like this. And the function, the current as a function of T is equal to I0 1 minus E to the power of T over, now this is, be careful, this is L over R, or I should rewrite this one as minus TR over L. When you have a current passing through L and you suddenly open the circuit, and you will have this here now. This is your I, and it starts from I0, and the current will exponential decay, and this is function of T, and this is I0 E to the power of T R over L. Okay, now for the capacitor RC circuit, we have a factor of T over RC, both in the charging and discharging case. For the RL case, it means resistor and inductor case, we have a exponential to the power of TR over L, this part and this part. So now first, let's look at some mathematics. In mathematics, if for any exponential function, the exponent here, it has to be a number. So this one is dimensionless. Now let's look at RC circuit. There's a function or the factor E minus T over RC. And we know the T is measured in seconds. So in order to become a dimensionless, it means the numerator is second. So the denominator, the unit of the denominator must also be in second. So they cancel out. So we can argue the unit of RC, when I put the bracket, I mean this is the unit of RC, must equal to second, because the unit of T is in seconds. So when they over, they are dimensionless. Now, the other way to look at this one is from the definition. So first, R is defined by Ohm's law, so it's a V over I. And capacitor is defined as charge per unit voltage. So when you multiply RC, you have V over I multiply Q over V. So this cancelled. But now think about what is I. The I is current. So is delta Q over delta T. Okay. So RC become Q over, or just say Q over T, and this is T. So the unit of RC is the unit of T second. For the inductor, E minus TR over L. Now we can rewrite this one as E minus T over L over R. So again, we have two parts. The numerator T is measured in second. So we are argue L over R. This one also must measure in second. So again, let's look at how L and R is defined. So R is defined as V over I. And how the L, inductance, is defined? Inductance is defined as the V across the inductor is proportional to the change of current, and the proportional constant is L. So now let's combine these two. From here first, L is V over di dt. So L over R is V over, now di dt, of course, we don't need to worry about delta. We can put the I here, we can put the T here, over the R is V over I. So you can say this is equal to T. So again, L over R is T, so the unit is second. Let's first look at the RC circuit. At the moment the switch is closed, current starts flowing from the battery. Now let's look at electrons. Now the electron will reach this side, but there's a gap here. But because of the induction, so this electron will repel another electron from the other side, and it causes a flow of current in the circuit. So this becomes positive because one of the electrons left. So more electrons will develop here, and there's a current flow here. So this is the time as if there's nothing here. So there will be a perfect conductor at the moment the switch is closed. And the current, the magnitude of the current, of course, if we look at from the conventional current side, this initial current is equal to V, the DC source, over R. So if we plot this one here, T, and this is the current, and this is I naught. However, this current will decrease because when more electrons accumulate here, this electron will try to opposite further electron coming here, because electron repels electron. At the same time, also, there's a voltage built up here. This voltage increase because more electrons and positive charge build up across the capacitor. And so what happens is this: the current will drop because there's an opposite potential build up, opposite further electron coming or accumulate across the capacitor. Usually we'll say when the time larger than 5 RC, this one will roughly equal to 0. So if we look at the voltage V, when it begins, the voltage is 0. But when the electron or positive charge start building up across the capacitor, the voltage increases, and until for T bigger than about 5 RC, it will reach 99% of the V naught, the DC source. So we will say this part and this part is the transient state, and this is the steady state. Now let's look at inductor. You have a V here when the switch close here. Now a current try to flow in. So when the current start flowing in here, it will create a magnetic field, and this magnetic field is from 0 to certain value. And the Faraday's law of induction say this change of magnetic field will create a voltage, and this voltage will try to against the current flow. So what it means is, at the moment you close the circuit, the current across here is actually 0. And it will rise static or exponentially, like the capacitor case, and reach I naught. And of course, I naught is equal to V naught over R. So the increase of the current will be static. And of course, after T bigger than 5, now this time, not the RC is L over R. This is the time constant for the inductor case. Now, how about the voltage? If we measure the voltage across the inductor, at the moment, the voltage is equal to the DC voltage. That's why when you close the circuit, you have a opposite voltage, opposite to the change. So the voltage is equal to V naught. But this voltage will exponential decay. So this is your transient state, and this is your steady state. The time constant for the RC circuit is defined as RC, and R is 10 to the times 10 to the power 3, and C is 47 times 10 to the power minus 6, and you will get 0.47 seconds. Now, if you have a DC source, if you have a switch, this is your R, and this is your capacitor C. Now, if you measure the voltage across the capacitor, when the switch is closed, this voltage of course increases, and this one is V, and when the time equal to 1 RC, Okay, 1 RC, one time constant. In this particular case, is 0.47 seconds. What value you have? Now first we need to know the equation. The equation is V T, and this is V naught, because you are charging 1 minus E minus T over RC. Now when T equal to tau or 1 RC, this one become the charge voltage 12, 1 minus T, this is T become RC, this is RC. So it doesn't really matter what RC it is, the most important is 1 RC. So this is 12, 1 minus E minus 1, and E to the power of minus 1 is equal to 0.368. Sometimes you can just use 0.37, it's good enough. So if you plug this one into your calculator, or before we do it, 1 minus 0.37, you can roughly 12, this is 0.63. So what I mean is, if this one is your DC source is 12 volt at 1 RC, it will reach 0.63 times 12. It means 63% of the DC source. That is the way you should remember. And if you plug it in, you will get the numerical value is 7.6 volts. But the important thing is this idea. You got 63%, you reach 63% of the voltage. This curve represents the discharge of a capacitor, and the equation describe this discharge is V T V naught E exponential to the power of negative T over RC. The voltage V naught is the initial voltage across the capacitor. It means when you already charge the capacitor, what is the original voltage you have. Now you connect this one to a resistor and a switch. When you close this switch, assume this is positive, this is negative, there's a current flow, and also the voltage across your capacitor will start to drop because you lose charge. Now if you look at the graph here, it's very clear the initial voltage is 1. So this one is Vt equal to 1 E minus T over RC. RC is the time constant tau. Next, we know a characteristic, which is when T is equal to 1 time constant, it means RC, so RC over RC minus 1, this is equal to 0.37. So what I mean is, when T equal to 1 time constant RC, your voltage will become 37% of the initial voltage. In this case, is 1 volt. This is our initial voltage. So we go back here, we try to find the y-axis. 0.37 is roughly about here. Now you reach 0.37, 37% of the initial voltage, 1 volt. That's why we find this number. And now we reach here, and now we reach here. What time? It is 1 second. So it's very clear now. The tau, the time constant, is equal to 1 second. Now, usually in practical engineering, they will say from 0 to about 3 time constant, we call this transient. It means it's still dropping. But when the time is bigger than 5 RC or 5 tau, we call this static state. It means already pretty much. Remember, when time larger than 5 RC, the voltage here is less than 1% of the initial voltage. When capacitor connected in series, so here 1, 2, 3. Now, what is the same? What is the difference? This is your external voltage. If this is positive, this is negative. This is positive, this is negative. Positive, negative, positive, negative. Next, the charge. Now, assume you have 1, 2, 3, 4 positive. The other opposite will also have 1, 2, 3, 4. And also for C2, there's also 1, 2, 3, 4. The reason is initially this must be neutral. This positive charge, you push the neutral side here, the positive charge from here to the other side here. So, but overall, if you look at here, this also neutral. So you will have negative, negative, negative. So it means the charge across each capacitor remains unchanged. So Q, Q, Q. But remember, one thing important is how we define capacitance. Capacitance is defined as charge per unit voltage. So the voltage is equal to Q over C. So you can see, because C1 may or may not equal to C2, or they may not equal. So the voltage across the 3 capacitors may or may not be equal, because I can say now V1 is equal to Q over C1. Each capacitor have the same charge, Q C2, Q C3. C1 is 10 microfarad, 20, and C3 is 30. So the voltage across here, V1, V2, and V3 will be different, but the charge is the same. 1 over C equivalent equal to 1 over C1 plus 1 over C2 plus 1 over C3. So 1 over C equivalent is equal to 1 over 10 micro. I drop the unit. 20, 1 over 30. And if you plug this one into a calculator, this is equal to 4.62 microfarad. We have 2 capacitors connected in parallel, C1 and C2. So this is C1, C2. And now this one will connect C3 in series. So to find their equivalent, we first find C1 and C2. Now this time, when the capacitors, they are connected in parallel, their equivalent is just the sum. So what I mean is, you can replace the 2 with 1 here, C3, and this one is equal to, we call the C pi, is just equal to C1 plus C2. So this one is 10 microfarad plus 20 microfarad is 30 microfarad. Now you have two capacitors connected in series. Their equivalent with capacitor C equivalent is 1 over C equivalent equal to, this time is you add them reciprocally. So this one is 30 micro plus 1 over 15 microfarad. So C equivalent is equal to 10 microfarad. One thing we want to look at is some of the characteristics of when two capacitors that are connected in parallel. Now this time, the voltage, I mean, if you look at here, if you measure the voltage across this one, we call V1, and measure the voltage across here, we call V2, they will be same. So whenever any component that are connected in parallel, they should have the same voltage. But this time, we have asked one question, which is, what's the difference? So C equal to Q over V. C1 and C2 could be different, but voltage is the same. So what I mean is, the charge will be different because charge is equal to CV. So how much charge stay on C1? So this is Q1 equal to C1V. How much charge across C2? So Q2 is C2V. They have the same voltage, but because C1 and C2 are different. So C2 is 20, is twice as much as C1. So the charge across C2 is double the charge across C1. We have three inductors connected in series. The equation is the same as resistors. So L equivalent is L1 plus L2 plus L3. So when you add this one, it becomes 100 millihenry. This question, we have a mixed inductor. So L1 and L2, they are connected in parallel. So this is L1, L2, they are connected in parallel. And then L3 in series. So L1, L2, L3. So the rule for inductor is the same as the rule for resistor. So we find the equivalent of L1 and L2. So they're in parallel. So this equivalent here will connect the L3. How about we call it L pi? So 1 over L pi equal to 1 over L1 plus 1 over L2. It means 1 over L pi equal to 1 over 10 milli plus 1 over 30 milli. And you will see this one equal to 6.67 millihenry. And L3 is equal to 60 millihenry. So their total equivalent this one is equal to the sum. We just add these two together. So this is 6.67 millihenry plus 60 millihenry. So it's 66.67 millihenry. This is the RC circuit, and the RC circuit is connected to a DC source. So this is 12 volt, and the R is 47 k ohm. Capacitor is 22 microfarad. And you want to find first is the time constant tau. Time constant tau is RC for RC circuit. So this is 47k times 22 mu. If you plug this one into your calculator, you will find 1.03 second. Okay. Now, what's the voltage across the capacitor at t equal to tau and 3 tau? So first write down the voltage across the C as a function of t equal to V0, the DC voltage, 1 minus E minus T to RC. So let's see, when t equal to tau, it means 1 RC. Vt is equal to V0, and in our case it's 12. 1 minus E. When t equal to RC, so this is minus 1. And if you plug this one in, you will find 0.37. And again, it means 63% of the 12. So you got 0.63 times 12. And you got 7.56 volts. Next, when t equal to 3 tau, 3 times of RC, Vt equal to 12, 1 minus E. Now this is minus 3 RC over RC, or 3 tau over tau, and this one is minus 3. So if you check your calculator, and you will find this one exponential to the power minus 3 equal to 0.0497, that's about 0.05. So 12, 1 minus 0.05. So 12 times 0.95. It means 95% of the 12 volts. So it means times, so 12 times 0.95, you got 11.4 volts. Now we have a RC circuit, and the R is 100 k ohm, and the capacitor is 47 microfarad. Now, when the switch closes, it's very clear it's discharged. So you want to find Vc. Okay, V, the voltage across the capacitor as a function of t, because it's discharged. So the equation is V0, the original voltage across the capacitor, exponential minus t over RC. So this time, what is RC? Let's check. The time constant RC is equal to 100k times 47 micro. So you will get 4.7 seconds. So V0 is 10 volts. So this is 10 volt. So we'll say the function should be written as 10 exponential minus t over 4.7. It is, understand, 4.7 is in second. Okay, so when the switch is closed, there will be a initial current flow, and the initial current flow will equal to I naught, and this is equal to V over R, and the V is the charge in the capacitor, which is 10. This one is 100K, and 10 over 100K. So we got 123.1 milliamp. Here we have a RL circuit, and the inductance is 50 millihenry. R is 100 ohm, and the voltage 12 volt. So when the switch is closed, there will be current flowing through, but the current will not go straight to the V over R, the steady state. It will rise. So if time, the current is function of t, it will rise like this, very similar to the charging against a capacitor, but this is the voltage, but this is the current, and this is I naught. Okay, I naught is equal to 12 over 100, and is equal to 0.12 amp. So this is 0.12 ampere. Okay, now the equation is described as the I as a function of t equal to I naught. So very similar to the case of capacitor. So this is 1 minus exponential minus t. Now this time again we put the time constant tau here, but the tau this time for the inductor RL case, the tau is defined as L over R. It's not RC, it's L over R. So let's calculate the time constant first. So the time constant L over R is 0.05 divided by 100. So you got 0.0005 second. Okay, so this is for the case of RL. Next, what is the current when the time equal to 1 hour, 1 time constant? This times RC is L over R. So when the current, when the time equal to L over R, it means 1 time constant. This is the maximum, is 0.12, 1 minus 1. So again, plug this one into a calculator, you got 0.076 ampere. When the time equal to 3 time constant, so 0.12, 1 minus E, this become minus 3. And plug this one into your calculator, you got 0.114 ampere. So at the time when the switch turns on, the current starts flow across the R. And remember, an inductor itself is a coil, so there's a current flow. But because the coil here, there will develop a magnetic field. This magnetic field, it depends on how you connect the coil. It can be flow to either way, But the most important is this magnetic field, we call the B field, increases. The Faraday law of induction says when the B field inside the coil increases, it will induce a voltage. Okay, this voltage, or we call EMF, some people call it back EMF. Why we call it back EMF? Because this voltage here will opposite the voltage. For example, if this is 12 volt, positive, negative, at the moment when you close the switch, this will be positive, this will be negative, and also you develop a 12 volt. So these two voltage try to opposite the change of the current. I mean, the current increase, it doesn't like the current increase. So the induced back EMF will opposite it. So at the moment when the switch is closed, the voltage is 12, same as the DC voltage. So you will find this curve here, T, and the voltage here is 12 volt, the voltage of your DC source, but it will drop, of course. And so as a function of T is 12, if this is the 12, exponential minus T over time constant, and the time constant is due to L over R. Okay. Now assume you have a circuit. It means you have this one is R, you have flow here. So there's a constant current flow to R and L. But L itself is like a coil. So there's no voltage drop in the ideal case, but you still develop a magnetic field inside the coil. But the magnetic field inside the coil won't change because the I is constant at this stage. So there's a static, and the I is equal to V over R, Ohm's law. Now what happened when someone decided to open the circuit? It means someone tried to open it. So when the time it opened, the current across the inductor suddenly drop. Again, when the current reduced, so the argument is like this, the current across here will drop. This change of current will cause the magnetic field from a constant to 0. It also drop. The change of magnetic field will create another voltage. Okay, it will try to keep the current flow. So what I mean is, if you look at the voltage across here, the voltage will suddenly increase, and then it will drop, of course, to 0 because later there's no current flow. And in terms of current flow, T, I, the same happens. It won't drop to the 0 immediately, so it will drop exponentially.